Okay. Um, let's see. Is it lying? Let's test it. Oh, it's not. All right. I have some Putnam problems to do. I still have physics research to do, and now I have some more adjustments to make. Um, uh, yeah, okay. So we're gonna do all of that. I obviously can't show my seismicity research at this stage anymore, so we're just gonna. Oh, okay. So let's do intensity. Let me put some music. I also need to make an AWS account for cloud. I don't really feel like it, but um, uh-oh. All right. What the heck? So much is going on. Oh, what am I doing? Oh, no, just kidding. I was like, huh? But no, good. Okay, yeah, I know what I'm doing. Let me also. I knew it was gonna pop up over there. Let me also. Oh, that's nice about earthquakes. Research can be so fun, and then sometimes it's like such a bore, such a drag. Some parts of the process are like immensely fun, you know? Some parts are just not immensely fun. Okay. Um, Wait, what? Why is the time formatted like that? Why is it? Hmm. There we go. Okay. Taking forever. Alright, I don't know what the heck this is doing. Bruh. I should get a stronger computer. Probably. It's fine. I also have some algorithm work to do. Putnam homework, algorithm homework, other stuff that I could be doing while this rots away. Algorithms. Alright, I'm getting coffee. I don't know what the heck it's doing. Alright, screw it. That's fine. I'll just do some, I don't know. point. That's kind of what I was excited to do. But it doesn't want to function. And I don't really have the patience for that not to function properly, so that's fine. Watch the algorithms like sure. Also, I'm waiting on some clearance for the website for a couple of things for the CC Me planner. So that's why we're working on this. Otherwise, I'd just be working on that, to be honest. But here we are. Bro, I'm about to just do my Putnam prep. Or I could have just done Andre's course. Sure. I mean, oh. Aww.
Welcome to machine learning. What is machine learning? In this class, you learn about the state of the art and also practice implementing machine learning algorithms yourself. You learn about the most important machine learning algorithm.
I'm sorry. No. just gonna watch this. Alright, first let's do algorithms. I don't really know if... Just, yeah.
Good morning, everybody. My name's Jason Koo.
What year was this? Oh, this was 2020. Oh, this was right before COVID.
Going to be teaching this class in Introduction to Algorithms.
Okay, wait, hold on.
Algorithms with two other instructors here, faculty in the department, Eric Demain and Justin Solomon. They're excellent people, and so
Why the heck is it doing that?
they will be working on
Okay. Bruh. Oof. Okay.
Teaching this class with me. I will be teaching the first lecture, and we'll have each of them teach one of the next two lectures, and then we'll go from there. Yeah, so this is Intro to Algorithms. Okay, so we're going to start talking about this course content now. What is this course about? It's about algorithms, right? Introduction to Algorithms. Really what the course is about is teaching you to solve computational problems. But it's more than that. It's not just about teaching you to solve computational problems. So solve, goal. 1, solve computational problems. But it's more than that. It's also about communicating those solutions to others and being able to communicate that your way of solving the problem is correct and efficient. Okay? So it's about two more things. Prove correctness, argue efficiency, and in general, it's about communication. I can't spell, by the way. Communication of these ideas. And you'll find that over the course of this class, you'll be doing a lot more writing than you do in a lot of your other courses. It really should maybe be a CI kind of class, because you'll be doing a lot more writing than you will be coding, for sure. So it's really important. Of course, solving the computational problem is important, but really the thing that you're getting out of this class and other theory classes that you're not getting in other classes in this department is that we really concentrate on being able to prove that the things you're doing are correct and better than other things, and being able to communicate those ideas to others and not just to a computer, right? To other people, convince them that it's correct. Okay, so that's what this class is about. So what do I mean when I say solve a computational problem? What is a problem? What is an algorithm? Right? I know people make fun of me because I start with this question, but I mean, anyone want to answer that question? No? What's a problem computationally? No? Okay, so it's not such a stupid question. Yeah? Something you want to compute. Okay, yes, that's true, right? But kind of a little bit more abstractly, what I'm going to think of a computational problem being, and this is where kind of your prerequisite in discrete mathematics should come in, right? It's a problem. set of inputs. Inputs. Okay, maybe I have 1, 2, 3, 4, 5 possible inputs I could have to my algorithm. Okay, then I have a space of outputs. Okay, outputs. And maybe, I don't know, maybe I have more of them than I do inputs, but these are the possible outputs to my, my problem. And what a problem is a binary relation between these inputs and outputs. Essentially, for each input, I specify which of these outputs is correct, right? It doesn't necessarily have to be one, right? If I say, give me the index in an array containing the value 5, there could be multiple 5s in that array, and so any of those indices would be correct. So maybe this guy maps to that output, and maybe this guy maps to, I don't know, 2 or 3 outputs, right? This input goes to 1, 2, I don't know. There's some kind of mapping here. These edges represent a binary relation. And it's kind of a graph, a bipartite graph between these inputs and outputs. And these are specifying which of these outputs are correct for these inputs. All right? That's really the formal definition of what a problem is. Now, generally, if I have a problem, a computational problem, I'm not going to specify the problem to you by saying, OK, for input 1, the correct answer is 0. And for input 2, the correct answer is 3, and so on and so forth. That would take forever, right? Usually what we do when defining a problem is specify some kind of predicate saying that, oh, we can check. If I give you an input and an output, I can check whether that output is correct or not. That's usually how we define a problem. If I am checking for whether this index contains a 5, I can just go to that array, look at index 5, and say, or the index you gave me, and see if it equals 5, right? So usually we're putting it in terms of predicates because in general, we don't really want to talk about small instances of problems. So let's say I had the problem of, among the students in this classroom, do any pair of you have the same birthday? Okay? All right, well, probably if there's more than 365 of you, the answer is yes. Right? Right? That by what? Pigeonhole principle, right? 2 of you must have the same birthday, right? But so let's generalize it a little bit. Say that, I don't know, I need a bigger space of birthdays for this question to be interesting. Maybe I tack on the year. Maybe I tack on the hour that you were born. And that's a bigger space of inputs, and I wouldn't necessarily expect that 2 of you would be born in the same year, on the same day, in the same hour, right? That would be a little less likely. In fact, as long as that space is larger than something like the square of the number of you, right, then I'm less likely than even to have a pair of you. That's a kind of a birthday problem you may have seen in 042. Potentially, right? But in general, I'm not going to mess with probability so much here. I want a deterministic algorithm, right? A way of checking whether 2 of you have the same birth time, let's say. Okay, so in general, in this class, we're not going to concentrate on inputs such as, is there a pair of you in this class that have the same birthday? That's kind of boring, right? I could just say, well, I could do a lot of different things, but what we do in this class, this is for a fixed classroom of you. I want to make algorithms that are general to any classroom, right? To go to your recitation, I want an algorithm that will apply to your recitation. I want an algorithm that not only applies to this classroom, but also the machine learning class before you, right? I want an algorithm that can change it can accept an arbitrarily sized input, right? Here we have a class of maybe 300, 400 students, right? But I want my algorithm to work for 1 billion students, right? Like maybe I'm trying to check if there's a match of something in the Facebook database or something like that, right? Okay, so in general, we are looking for general problems that have arbitrarily sized inputs, right? So these inputs could grow very large, but we want a kind of a fixed size algorithm to solve those problems, okay? So what is an algorithm then? What am I? No. I really can't spell. I told you. Okay. I didn't lie to you. So an algorithm is a little different than a problem. A problem specification, I can state to you what this graph, or I can tell you what this graph looks like. An algorithm is really, I don't know what the outputs are. I don't know what these edges are. But I want a fixed size kind of machine or procedure that if I give it an input, it will generate an output. And if it generates an output, it better be one of these correct outputs, right? So if I have an algorithm that takes in this input, I really want it to output this output, or else it's not a correct algorithm. Similarly, if for this one, it could output any of these three outputs, but if it outputs this guy for this input, that would not be a correct algorithm, right? And so generally what we want is an algorithm is a function. It takes inputs to outputs, right? An algorithm is some kind of function, right, that takes these inputs, maps it to a single output, and that output better be correct based on our problem, okay? So that's what our algorithm is. It solves the problem if it returns a correct output for every problem input that is in our domain, okay? And the example for, does anyone have a possible algorithm for checking whether any two of you have the same birth time as specified before? I'm going to let someone else have a try. Sure.
Just ask everyone one by one, and every time check if you earned the birth.
Ah, great. So what your colleague has said is a great algorithm. But essentially what it's going to do is I'm going to put you guys in some order. Okay? I'm going to give each of you a number, 1 through however many number of students there are in this class. And I'm going to interview you one by one. Right? I'm going to say, what's your birthday? And then I'm going to write it down. Right? I'm going to put it in some kind of record. Okay? And then as I keep interviewing you, I'm going to find out your birthday. I'm going to check the record. I'm going to look through all the birthdays in the record. If I find a match, right, then I return, yay, I found a pair, and I can stop. Otherwise, if I get through the record list, I don't find a match, I just stick you at the end of the record, right? I add you to the record, and then I move on to the next person. I keep doing this. Okay, so that's a proposed algorithm for this birthday problem. For birthday problem, what's the algorithm here? Maintain a record. Interview students in some order. And what does interviewing a student mean? It means two things. It means check if birthday in record. And if it is, return a pair. So return pair. Otherwise, add new student to record. And then at the very end, if I go through everybody and I haven't found a match yet, I'm going to return that there is none. Right. Okay, so that's a statement of an algorithm. That's kind of the level of description that we'll be looking for you in the theory parts of this, theory questions that we ask you on your problem sets, right? It's a verbal description in words that, it's maybe not enough for a computer to know what to do, but if you said this algorithm to any of your friends in this class, right, they would at least understand what it is that you're doing. Yeah? Pure function in the, does an algorithm have to be a pure function in the mathematical sense? in it needs to map to a single output?
As in, it can't modify some external state, it can't take in a state, it can't do I/O.
So we're talking about kind of a functional programming definition of a function, right? This is I am talking about the mathematical. I have a binary relation, and this thing has an output for every input, and there is exactly one output to every input. That's the mathematical definition of function that I'm using for when I'm defining an algorithm. Yeah.
Hold on, I think I'm gonna switch over to my what's it called? Research. Hold on, let me do this research, and then I'll come back to this because I'm not gonna be able to focus if I don't have this research done this week. I won't be able to eat. I won't be able to sleep. Okay, let me see. Oh, wait. Oh, yes, I see. Okay, yes. Okay. Okay, let's see. With these new plots. Get some fun. I need to get one of those to look at my, what's it called? I need to get one of those things that like blows the dust out of this because this looks egregious. I don't want to get my drink. This is actually crazy though. How much like stuff is in here? I need like a air. I think I have one in the lab. Alright, let's see. Okay, so here is the distribution. No, just kidding, that's still. No, I need the histogram of the velocity values with a Gaussian fit. Why the heck does it look like that? Oh, I was like, huh? Oh, I had to scroll. Okay. Observe velocity, and then here's the. Okay. Same thing here. Okay. Huh? Why is it like this? Oh, it's gotta be. Oh, why is it? Oh, wait. Why is it like that? Hello? Okay. Um. What the freakle? Okay. I haven't done this research since 16th of June. But it's okay. My professor and I both have been on a break. Let's chill. Hello? Why do I keep doing that? I keep accidentally clicking Command N. Okay. Oh my goodness. I need to make like the research folders. Alright. Alright. Now I've done my research. Now I can actually focus on this. Make sure I save everything. Okay. That actually takes a huge load off my back. I can actually focus on this.
Basically is an algorithm like a plan?
Yeah, an algorithm's a procedure that somehow I can do whatever I want, but I have to take one of these inputs and I have to produce an output, and at the end it better be correct. Right? So it's just a procedure. You can think of it as like a recipe. You can think of it as, it's just some kind of procedure, right? It's a sequence of things that you should do, and then at the end you will return an output. Okay, so here's a possible algorithm for solving this birthday problem. Okay? Now, I've given you what I argue to you, or I'm asserting to you, is a solution to this birthday problem. And maybe you guys agree with me, and maybe some of you don't, right? So how do I convince you that this is correct, right? Well, if I had, if I was just running this algorithm on, say, the 4 students in the front row here, right, I could argue it pretty well to you. I could go through I could assign these 4 people birthdays in various combinations of either none of them have the same birthday, some 2 of them have the same birthday. I could try all possibilities, and I could go through lots of different possibilities. I could just check that this algorithm returns the right answer in all such cases, right? But when I have, 300 of you, that's going to be a little bit more difficult to argue. And so if I want to argue something is correct in mathematics, I want to prove something to you for some large value, what kind of technique do I use to prove such things? Yeah, induction, right? And in general, what we do in this class, what we do is, as a computer scientist, is we write a constant size piece of code, right, that can take on any arbitrarily large size input, right? If the input can be arbitrarily large, but our code is small, then that code needs to loop or recurse or repeat some of these lines of code in order to just read that output, right? And so,
I've always wondered, is recursion just repetition? Recursion in programming is just the repeated act of doing something. Oh, that's recursion. Interesting. I did not know that. Actually, let me write this on different.
that's another way you can arrive at this conclusion, that we're going to probably need to use recursion, induction, and that's part of the reason why we ask you to take a course on proofs and inductive reasoning and discrete mathematics.
There's induction, contradiction. Oh, there's direct proof. Proof by cases. Proof by induction. Proof by strong induction.
Mathematics before this class. Okay, so how do we prove that this thing is correct? We got to use induction. So how can we set up this induction?
Oops. Bless you.
What do I need for an inductive proof? Sure. Base case, we need a base case. We need some kind of a predicate, yeah, but we need some kind of statement of a hypothesis of something that should be maintained, right? And then we need to have an inductive step, which basically says I take a small value of this thing. We need to of a hypothesis of a predicate, yeah, but we need some kind of statement of a hypothesis of something that should be maintained, right? And then we need to have an inductive step, which basically says I take a small value of this thing, I use the inductive hypothesis, and I argue it for a larger value of my well-ordered set that I'm inducting over, right? Okay, so for this algorithm, if we're going to try to prove correctness, what I'm going to do is I'm going to, what do I want to prove for this thing? That at the end of interviewing all of you, that my algorithm has either already, it has returned with a pair that match, or if we're in a case where there wasn't a match, wasn't a pair somewhere in my set, that it returned none, right? That would be correct, right? So how can I generalize that concept to make it something I can induct on, right? What I'm going to do is I'm going to say, let's say after I've interviewed the first K students, right? If there was a match in those first K students, I want to be sure that I've returned a pair, right? Because if after I interview all of you, I've maintained that property, then I'll be sure at the end of the process I will have returned a pair if one exists. So here's going to be my inductive hypothesis. Cis. Okay. If first K students contain a match, algorithm returns a match before interviewing, say, student
K plus 1.
K plus 1.
Student K plus 1 is like
Okay,
the
so
next
that's going to
student,
be my
right?
inductive hypothesis. Now,
Okay, so my thought process is K is the current student, K plus 1 is the next student. So if I'm talking to you and I'm currently interviewing you, you're K. The person behind you is K plus 1. So who in the heck is K prime? Assume for induction hypothesis holds for K equals K prime. I guess we brought you back up. So why would we bring you back up? Why would we bring you back up? And consider K is equal to K prime plus 1. If first K prime contains a match already returned a match by induction, else first K prime does not have a match, so if first K prime plus 1 has a match, match contains K prime plus 1. Then algorithm checks directly whether birthday of K prime plus 1 exists in the first K. Oh, I guess I brought you back up. I guess I cycled through again. Why would I do that? Oh, I guess Hmm. Somebody lied? I mean, I don't know.
If there's n students in this class, right, and at the end of my thing, I'm trying to interview student n plus 1. Oh, student n plus 1's not there. If I have maintained this, then if I replace k with n, then I will have returned a match before interviewing the last student, or when I have no more students left. And then this algorithm returns none, as it should, right? Okay, so this inductive hypothesis sets up a nice variable to induct on, right? This k I can have increasing up to n, starting at some base case. So what's my base case here?
Would it just be K? Whoever that first student is?
My base case is the easiest thing I can do, sure. 2, that's an easy thing I could do. I could check those possibilities, but there's an even easier base case, yeah. There's an even easier base case than 1. 0, right?
Oh, so he wanted a
0
quantity.
students, I haven't done any work, right? Certainly the first 0 can't have a match, right? And so this predicate, this inductive hypothesis, is true
when k is greater than or
initial
equal to 2.
False, right? So I can say, you know,
because
base case
if k is 0, if you have 0 students, you didn't find a match. So your algorithm is. If k is equal to 1, a match requires 2 students to have the same birthday. So does this mean k has to be equal to 2? What is the point of a base case?
Zero, check. Definitely this predicate holds for that. Okay. Now we get to go for the meat of this thing, right? Assume the inductive hypothesis true for k equals, say,
Yeah, I
some
don't
k
know,
prime.
brother.
Okay, and we're considering k prime plus 1, right? Then we have 2 cases. One of the nice things about induction is that it isolates our problem to not consider everything all at once, but break it down into a smaller interface so I can do less work at each step, right? So there are 2 cases. Either the first k already had a match,
Oh.
right? In which case, by our inductive hypothesis, we've already returned a correct answer, right?
Right.
The other
Now
case is it doesn't have a match, and we interview the k plus 1th student, the k prime plus 1th student. If there is a match in the first k prime plus 1 students, then it will include k prime plus 1, the student k prime plus 1, because otherwise there would have been a match in the things before it, right? So there are 2 cases. If k contains match k prime, if first k contains match, already returned, turned by induction, right? Else, if k prime plus 1 students contains match, the algorithm checks all of the possibilities. K prime checks k against all students, essentially by brute force. It's a case analysis. I check all of the possible possibilities, right? This check if birthday is in record. I haven't told you how to do that yet, but if I'm able to do that, I'm going to check if it's in the record. If it's in the record, then there will be a match and I can return it. Otherwise, have reestablished the inductive hypothesis for the k prime plus 1 students. Does that make sense, guys? Yeah. Okay, so that's how we prove correctness. This is a little bit more formal than we would ask you to do in this class all the time, but it's definitely sufficient, for the levels of arguments that we'll ask you to do.
What is K prime here? Like, I think that's the part where I'm like, huh? Like, what is K prime here? K is the number of students already in the record. Oh, so K is, okay. So then K plus 1. Okay. Yes, I understood the base case. Yeah. So this is like everybody in line. K naught plus 1 is the next student. Okay.
Bar that we're usually trying to set is if you communicated to someone else taking this class what your algorithm was, they would be able to code it up and tell a stupid computer how to do that thing. Okay? So, any questions on induction? You're going to be using it throughout this class, and so if you're unfamiliar with this line of argument, then you should go review some of that. That would be good. Okay, so that's correctness, being able to communicate that the algorithm we stated was correct. Now we want to argue that it's efficient, right? What does efficiency mean? Efficiency just means not only how fast does this algorithm run, but how fast does it compare to other possible ways of approaching this problem, right? So how could we measure how fast an algorithm runs? This is kind of a silly question, yeah? Yeah, just record the time it takes for a computer to do this thing, right? Now, there's a problem with just coding up an algorithm, telling a computer what to do, and timing how long it takes. Why? Yeah. It would depend on the size of your data set. Okay, we expect that, but there's a bigger problem there. Yeah? It depends on the strength of your computer, right? So I would expect that, if I had a watch calculator and I programmed it to do something, right? That might take a lot longer to solve a problem than if I asked, IBM's research computer, right, to solve the same problem using the same algorithm, even with the same code, right? Because its underlying operations are much faster, right? How it runs is much faster. So I don't want to count how long it would take on a real machine. I kind of want to abstract the time it takes the machine to do stuff out of the picture. What I kind of want to say is, let's assume that each kind of fundamental operation that the computer can do takes some fixed amount of time, okay? How many of those kinds of fixed operations does the algorithm need to perform to be able to solve this problem, right? So here we don't measure time. Instead, count kind of fundamental operations, okay? We'll get to what some of those fundamental operations are in a second, but the idea is we want a measure of how well an algorithm performs, not necessarily an implementation of that algorithm, right? Kind of an abstract notion of how well this algorithm does. And so what we're going to use to measure time or efficiency, right, is something called asymptotic analysis. Anyone here understand what asymptotic analysis is? Probably, since it's in both of your prerequisites, I think. But we will go through a formal definition of asymptotic notation in recitation tomorrow, and you'll get a lot of practice in comparing functions using an asymptotic analysis. But just to give you an idea, right? The idea here is we don't measure time, we instead measure ops, and like your colleague over here was saying before, we expect performance. I'm going to use performance instead of time here. We expect that to depend on size of our input, right? If we're trying to run an algorithm to find a birthday in this section, we expect the algorithm to run in a shorter amount of time than if I were to run the algorithm on all of you, right? So we expect it to perform differently depending on the size of the input, and how differently is how we measure performance relative to that input. Usually we use n as a variable for what the size of our input is, right? But that's not always the case. So for example, if we have an array that I give you, an n by n array, right? That we're going to say n, but what's the size of our input? How much information do I need to convey to you to give you that information? It's n squared, right? So that's the size of our input in that context, right? Or if I give you a graph, it's usually the number of vertices plus the number of edges. That's how big, how much space I would need to convey to you that graph, that information. Okay, so we compare how fast an algorithm is with respect to the size of the input, right? And if that, we will use the asymptotic notation. We have big O notation, which corresponds to upper bounds. We'll have omega, which corresponds to lower bounds. And we have theta, which corresponds to both, right? This thing is tight. It is bounded from above and below by a function of this form. Okay? Now we have a couple common ways, a couple common functions that algorithms, their running time, we have a couple common functions that relate an algorithm's input size to its performance. Some things that we saw all the time. Can anyone give me some of those? Say again?
Insert tabs.
Sorry. So like a function, I'm not asking this question well, but has anyone heard of a linear algorithm? A linear time algorithm, right? That's basically saying that the running time of my algorithm, the performance of my algorithm is linear with respect to the size of my input, right? Yeah. Say again? Like putting something in a list. Okay, so there's a lot behind that question that we'll go into later this week. But that's an example of if I do it in a silly way, I stick something in the middle of a list and I have to move everything, that's an operation that could take linear time, right? Okay. So linear time is a type of function. We've got a number of these. I'm going to start with this one. Does anyone know what this one is? Constant time. Okay. Basically, no matter how I change the input, the amount of time this running time, the performance of my algorithm takes, it doesn't really depend on that. Okay. The next one up is something like this. This is logarithmic time. Okay. We have theta n, which is linear, n log n, right? Sometimes we call this log linear, but we usually just say n log n. Okay. We have a quadratic running time. In general, if I have a constant sometimes we call this log linear, but we usually just say n log n. Okay. We have a quadratic running time. In general, if I have a constant power up here, right? It's n to the c for some constant. This is what we call polynomial time, right? As long as c is some constant. And this right here is what we mean by efficient in this class usually, right? In some other classes, right, when you have big data sets, maybe this is efficient, right? But in this class, generally what we mean is polynomial, and as you get down this thing, things are more and more efficient, okay? There's one class I'm going to talk to you about over here, which is something like, let's do this, 2 to the theta of n, right? Exponential time, this is some constant to a function of n that's, say, superlinear. That's going to be, say, superlinear. That's going to be, pretty bad. Why is it pretty bad? If I were to plot some of these things, as a function of n, right? Let's say I plot values of up to 1,000 on my n scale here. Okay? What does constant look like? Maybe this is 1,000 up here too. What does a constant look like? Looks like a line, right? It looks like a line over here somewhere. It could be as high as I want, but eventually anything that's an increasing function will get bigger than this, right? And on this scale, if I use log base 2 or some reasonable small constant, what does log look like? Well, let's do an easier one. What does linear look like? Yeah, this, right? That's what I saw a lot of you doing. Okay? That's linear. That's the kind of base that we're comparing everything against. What does log look like? Like this. Okay. But at this scale, right? At this scale, really, it's much closer to constant than linear. And actually, as n gets much, much larger, this almost looks like a straight line. It almost looks like a constant. So log is almost just as good as constant, right? What does exponential look like? It's the exact inverse of this thing, right? Right? It's almost an exact straight line going up, right? So this is crap. This is really good. Almost anything in this region over here is better, right? At least I'm gaining something. I'm able to not go up too high relative to my input size. So quadratic, I don't know, is something like this, and n log n is something like this. N log n, after a long time, really starts just looking linear with a constant multiplied in front of it, right? Okay, so these things good, that thing bad, okay? That's what that's trying to convey. All right, so how do we measure these things if I don't know what my fundamental operations are that my computer can use, right? So we need to define some kind of model of computation for what our computer is allowed to do in constant time, in a fixed amount of time, right? In general, what we use in this class is a machine called a word RAM, which we use for its theoretical brevity. All right, word RAM is kind of a loaded term. What do these things mean? It means I have, does someone know what RAM means? Random access memory, right? It means that I can randomly access different places in memory in constant time. That's the assumption of random access memory. Basically, what our model of a computer is you have memory, which is essentially just a string of bits. It's just a bunch of ones and zeros, right? And we have a computer, like a CPU, right, which is really small. It can basically hold a small amount of information, but it can change that information, right? It can operate on that information, and it also has instructions to randomly access different places in memory, bring it into the CPU, act on it, and read it back. Does that make sense? But in general, we don't have an address for every bit in memory, every 0 and 1 in memory. We actually, does anyone know how modern computers are addressed? Yeah. Okay, so we're going to get there. Actually, what a modern computer is addressed in is bytes, okay, collections of 8 bits. So there's an address I have for every 8 bits in memory, consecutive 8 bits in memory. And so if I want to pull something into the CPU, I give it an address. It'll take some chunk, right, and bring it into the CPU, operate it on it, and spit it back, okay? How big is that chunk? This goes to the answer that you were asking, or saying, which is it's some sequence of some fixed number of bits, which we call a word. Okay? A word is how big of a chunk that the CPU can take in from memory at a time and operate on. Okay? In your computers, how big is that word size? 64 bits. right? That's how much I can operate on a time. When I was growing up, when I was your age, okay, my word size was 32 bits. And that actually was a problem for my computer because in order for me to be able to read to address in memory, I need to be able to store that address in my CPU in a word, right? But if I have 32 bits, how many different addresses can I address? I have a limitation on the memory addresses I can address, right? So how many different memory addresses can I address with 32 bits? 2 to the 32, right? That makes sense. Well, if you do that calculation out, how big of a hard disk can I have to access? It's about 4 gigabytes, right? So in my day, all hard drives were limited to being partitioned. Even if you had a bigger than 4 gigabyte hard drive, I had to partition it into these 4 gigabyte chunks, which the computer could then read onto, right? That was very limiting, actually. That's a restriction. With 64 bits, what's my limitation on memory that I can address? Byte addressable. Turns out to be something like 20 exabytes. To put this in context, all data that Google stores on their servers, on all drives throughout the world, it's about 10. Right? So we're not going to run out of this limitation very soon, right? So what do we got? We've got a CPU. It can address memory. What are the operations I can do in this CPU? Generally, I have binary operations. I can compare 2 words in memory, and I can either do, integer arithmetic, kind of logical operations.
Oh,
Bitwise
he's coming
operations.
back to it. I was like, he kind of skipped
We're not going to use
processor.
those so much in this class. And I can read and write from an address in memory, a word, in constant time. Those are the operations that I have available to me on most CPUs. Some CPUs give you a little bit more power, but this is generally what we analyze algorithms with respect to, okay? But you'll notice that my CPU is only
Running
built
out
to
of
operate
space.
on a constant amount of information at once. Generally, 2 words in memory.
My algorithm page.
An operation
I don't know why I
produces a
did
third
this,
one,
but I
and
have
I
paper,
spit it out,
but-
right?
I just wanted to do it.
It takes a constant amount of time to operate on a constant amount of memory. If I want to operate on a linear amount of memory, n things, how long is that going to take? Right? If I just want to read everything in that thing, it's going to take me linear time, right? Because I have to read every part of that thing. Okay? So in general, what we're going to do for the first half of this class, mostly, first 8 lectures anyway, is talk about data structures. And it's going to be concerned about not operating on constant amount of data at a time, like our CPU is doing, but instead what it's going to do is store a large amount of data and support different operations on that data, okay? So if I had a record that I want to maintain to store those birthdays that we had before, I might use something like a static array, right, which you guys maybe are not familiar with if you have been working in Python as your only programming language, okay? Python has a lot of really interesting data structures like a list and a set and a dictionary and all these kinds of things that are actually not in this model. There's actually a lot of code between you and the computer, and it's not always clear how much time that interface is taking, right? And so what we're going to do starting on Thursday is talk about ways of storing a non-constant amount of information to make operations on that information faster. So just before you go, I just want to give you a quick overview of the class. To solve an algorithm problem in this class, we essentially have 2 different strategies. we can either reduce to using the solution to a problem we know how to solve, or we can design our own algorithm, which is going to be recursive in nature. We're going to either put stuff in the data structure, we're going to solve a sorting problem, or search in a graph. And then to design a recursive algorithm, we have various design paradigms.
Wait, reduce. Oh, there's two different. All right, should I watch lecture 2? Or should I go watch this introduction to neural nets and deep learning? Decisions, decisions, decisions. Decisions, decisions, decisions. Hmm. Oh, wait, but that's... Let me see. This would probably be in what? What degree program would this be in? In their degree chart. This would definitely be in School of Science. Course 6 and 15. That's course 18. What's course 15? Why are they not in alphabetical order? Or is it interdisciplinary? Oh, that's like... maybe. Engineering? Do they consider... I just need course 15. Hopefully I don't pass it because it's like... very easy to pass. They're in odd orders. That's fine. I don't know why I just didn't do this. Huh. That's not right. That's not right. Okay. Let me think. Let me just do subjects. That might pan out better. Thinking it's gonna be this one. I think it's gonna be either this one or it's gonna be in this. I think that's pretty much, that's it. Yeah, because here's our 6.5. Software engineering, fundamentals of programming, programming languages, theoretical computer science, discrete. See, if I would have known this, honestly, I would have taken, excuse me, discrete mathematics right after calculus 1, for sure. Advanced algorithms. We're like in the... Let's see, how far up does this go? Because... yeah, poker bots. I think we're too in the weeds. It's engineering. Oh, see, like here's NLP. Computer vision. So then what is computational science engineering? I don't know why I did this. I really just wanted to see the prereqs for this because yeah, what are the prereqs? Okay, let me stop because if not, then I'm not gonna want to do that anymore. I might go watch the proof. I love. I might watch this now and do some proofs. I actually need to know proofs. I love Professor Abel. He's so cool, dude. I remember watching him in his
6120. I don't know how you want to.
I remember watching him in his documentary that they did on him when he was like in high school. Of like the journey to the IMOs. It was awesome.
Pronounce it. Anything goes. Either way, welcome.
I think I've already done all this.
Skills.
Right, 'cause this is where they're just
How do we
talking
determine
through.
truth?
I think I did all of this, actually.
More.
Okay, wait. They've lost me now.
Sorry. Even easier example. P is prime. Is that a proposition? I'm seeing some thumbs down. I'm seeing some thumbs down. Yeah, it's not a proposition. Not a proposition. Because it's sort of incomplete information. What P are we talking about? If you tell me a P is 7 prime, that's a proposition. Is 12 prime? That's a proposition. So this is sort of a proposition with a variable that we need to fill in before it becomes a proposition. This is what's called a predicate. This is a predicate.
Okay. I'll come back to this. I might here too. Where's my no? Oh, I almost fell on my seat. Okay, proof writing. Am I sure this is proof writing? It looks like this. Oh, looks like it transferred over. That's fine. My to-do list. I'm gonna really quickly rewrite all the proof writing stuff, and then continue with that. I'm just gonna rewrite it. Look, you're hurting my head. Whoops. This is kind of tiring, not gonna lie. Oh boy. I think it's good to rewrite your notes. Like now this stuff is really sticking, you know, but oh my gosh, it's tragic. Honestly, not bad. I'm not gonna lie. For the week, that's probably like it's pretty decent. I was a little behind on certain stuff, but I still like, you know, powered through. So I'm not mad at it at all. Continuing on. Cardinality. Oops. That line's kind of ugly. sugar. Okay, great. Now that's all right now. This back in. I might do it right. But now continue. Okay. I have to be very strategic now. My parents are like an hour away. I'm gonna work on my Putnam problems. This will be what I work on. I don't even know what's happening. I'm gonna come back and look at this. Don't know. I'm gonna look at my Putnam problems. Get a couple more sheets of paper. Might need it. Oh, I have this to do. I might just read. I have no idea, to be honest. I kind of still want to read. I feel like to cap off this week, like I just want to read my deep work book. I really do. I think that's what I'm gonna do. I'm gonna read my deep work book. I'll write out the problems if anything comes to me. Yeah, but okay. So what problems did we go over? I can't even know what problem this is. It's from the list of easy Putnam problems. Okay. I'm just gonna write these down and then I'll look at the deep learning book. Okay, it was this one, this one, this one, and this one. Okay. Method of thinking. Alright. So let's start at the top. Try and give like a page to everything. So for problem 2024 A1, determine okay. First thing for this one that I'm gonna... Dang, where's my special pencil? First thing that I'm gonna note for this problem is when kind of discussing what I would do with my professor, it reminds me of the Pythagorean theorem. I think that's the first step in any of these simple problems, is to see if I can find some sort of connection to some formula, some relationship, some equation that I know. This one immediately said Pythagorean theorem. Or if I can just think of some basic operation to do to make things simpler. So this one, Pythagorean theorem, that's a step in the right direction. This one, I actually really like the way this one is. I'll explain it once I get there, but I actually enjoyed talking to him about this one. I never thought I'd actually like the problem, but I like this one. This one, we talk about like this kind of incited the conversation of deriving equations and what does that mean and why do we derive equations? What's the point? So yeah, we're gonna do this. And I really like this one too. I like the 2018 one. This is the one where it's like, what's the simplest course of action? So yeah. And it's good that I do this now too, because I'm pretty good at forgetting things if I don't do them immediately. That's why I've got papers from the office of what we did. And yeah. It also helps that like whenever we reach a crossroad, he always is like, let me write it down. Let me get my... Let's see. Where's my special pencil? Oh, that's another thing I need to write in this algorithm book. Because I asked him, why is it they're always saying non-increasing, or they'll say non-decreasing. Instead of being like, this array, we want to take this array and we want to use an algorithm, put it in increasing order, it'll be like non-decreasing. And he told me it's because non-decreasing stands for increasing or constant. So I have to write that down, or else I will forget. When I go and read this and I look at it again, I'm like, oh, why are they writing right there? Order of growth, algorithms, insertions, sort. Have I gone too far? I think so. No, I'm still in selection sort. No, I think I've gone too far. Where did it say non-increasing and decreasing? I think I've gone. No, I've gone too far. Like in the very beginning, I remember. It's not increasing. All right, perfect. Good stuff. So, pencil. Gosh. Goldfish brain. I don't think my pencil's in here. Where's my favorite pencil, dude? That's still my pencil. Where's my rotary? Let's see. I haven't used that. Oh, too late. I'm not using that. This too. Oops. Alright. What do we got going on here? I don't want to do my work. Not me. Okay. So with problem 2024A, first thing that comes to mind for brain dump is this has a Pythagorean theorem format. And then what else do we know? We have coefficients that are increasing. Well, they increase each term. So what do we need to do? We basically need to plug in n. We need to plug in n's and evaluate this equation and record our outputs. And also n cannot be equal to 0 because it doesn't. Positive integers, n equals 0 is not a positive. All right, that's kind of the basis for that one. I actually feel pretty good with that one. Next problem. I picked out like 4 of them. We'll do problem. Which one comes next? 2023. Yeah. So now it's problem 2023. I've noticed a lot of the ones that I enjoyed were A1s. I wasn't really a fan of B. But Okay, and this one is for a positive integer. Oh my gosh, how loud am I talking? I forget these are like noise canceling. Bruh. Okay. For a positive integer n, let f sub n. What am I looking at right now? Yeah, I almost wrote that wrong. X be equal to cosine x. There's a couple things to keep in mind, especially with this problem. All right, I actually really like this problem. Here's why. First and foremost, we're taking derivatives. Which is great. Second of all, there is a product rule here. I think this problem would be immensely easier, so much easier, if this was addition and we were taking derivatives, because that would just be a no-brainer. It would just be 1 plus 2 plus 3 plus da 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 until you get to a number that's greater than 2023. But this is a product rule, which means that we know if we have f of x times g of x times, well, this is almost like an f of g of n of x. There's so many subsequent derivatives here. But let's just say we did f of x, g of x, and let's say we wanted the derivative of this. Well, how do we denote? Oh, I remember. Okay, so let's do d over dx of all of that. We know would just be f prime of x times g of x plus f of x g prime of x. Okay, but let's say, okay, yeah, we have to find the smallest n. So for instance, let's do an example calculation. So if we assume, well, first, let's say f of 8 of x, right? Then what this looks like with that dot, dot, dot is there's things that go in between. This dot, dot, dot means that there are terms that must fill in this area. So it's terms to be filled in based on what n is equal to. So if we had f of 8, then we'd be looking at cosine of x, cosine of 2x, cosine of 3x, and I'm going to write them all out. Cosine of 4x, cosine 5x, cosine of 6x, dot, 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 cosine of 7x, cosine of 8x. Similarly, if we had, let's say we only did f of 2x, well then we would just get cosine of x and cosine of 2x. Okay, so let's say we wanted to evaluate, just as an example of how this would work. So let's say we want to evaluate f of 1. Okay, great. That's just going to be cosine of x. Then we would do f prime of 1 of x, which we know would be negative sine of x. Great. Then we would take f double prime of 1 of x, which we know would be a negative cosine of x. And now we know we have to plug in whatever f prime of 1 of 0. And we know negative cosine, well, we know that cosine of 0 is just equal to 1. And then, so we just get a negative 1. Finally, we have to take the absolute value of f of 1 of double prime of 0, which is just going to give us a 1. And we know that 1 is indeed, where are we at? Less than 2023. So we know that n is, no, we know that n equals 1 is not the smallest n, right? We know that n equals 1 is not the smallest n to satisfy. It's actually way too small to satisfy this. Now here's what's going to be interesting. Now let's say I evaluate, because I didn't do it in the office. I had another question to ask. Let's say I do f of 2 of x, which would be cosine of x, cosine of 2x. Well, if we take the derivative of this, we get a negative sine of x, cosine of 2x, plus a cosine of x. What is that? That's a negative, is that a negative 2 sine of 2x? Because isn't that a chain rule? Let me see. So, isn't that a chain rule? Yeah, so it is negative 2x. Okay, so now we basically have negative sine of x cosine of 2x minus, I'm going to put my signs in the front, minus 2 sine of 2x times cosine of x. And that's only the first derivative. So now we go ahead and calculate the second derivative, which is going to be negative cosine of x cosine of 2x plus, oh my gosh, negative sine of x times a negative 2 sine of x plus okay, now I gotta think for real, because the derivative of this, we're gonna have a negative cosine, but is it that, can I leave that with that? Okay, let me do something. I'm getting wonky. We're gonna have a negative times a negative 4 cosine of 2x. Let me do it like that. And this is still going to be associated with a cosine of x. Then we're going to add this negative 2 sine of, whoa, where am I? Negative 2 sine of 2x. And then, okay, yeah, now it's going to be multiplied by a negative sine of x. Oh my lord. Okay, hopefully this is right. So then we would have negative cosine of x cosine of 2x Oh, I don't think that matters. I was like, what do I do with this sine squared? But I don't think this matters. So let's just go minus sine of x times a negative 2 sine of x. Where am I at now? Okay, and do that plus 4 cosine of 2x times cosine of x plus 2 sine of 2x times a positive sine of x, because 2 negatives make a positive. Holy moly. Okay, then we would just take the f double prime of 2 and insert a 0, plug in 0, so we would get negative cosine of 0 times cosine of, gosh, that's just going to be 2 times 0. Oh my. Minus sine of 0 times a negative 2 sine of 0 plus 4 cosine of 2 times 0. What line am I on? Okay, yeah. Cosine of 0 plus 2 sine 2 times 0 sine 0. Okay, this is just going to give me a, it's going to go to 0. This is just going to be a negative 1. That's all going to go to 0. A negative 1 plus 4. Oh my gosh. Oh my gosh. A negative 1 plus 4. And then if we were to take the absolute value of this, we would get 5. And if we know that for all of our marbles, for all of that work that we did, 5 is less than 2023. So n equals 2 is too small. I'm scared because that was a lot. Let me see if I can. Is this possible? Can I do this? Can I do? I just want to see what it would be. How do I even express this? Just to make sure that, let me see, how do I express this? Without getting the answer, of course. How do I express, okay. How do I express the second derivative of the absolute value of f of 0, where f of x is equal to cosine of x cosine 2x. Oh my. Hopefully they understand what I'm saying. There is an identity. That's what I told Dr. All. I was like, I feel like there's an identity we can use here. Okay, so there's an identity I can use. Because that's exactly what I got. I got negative 5. Okay, so wait. This is actually... That's not the absolute value, though. How's it going to... if I know how to type, I'd be dangerous. Oh, it says it right here. The absolute value does not affect the second derivative at 0. Interesting. Hmm. So when this is greater than 0, the absolute value does not change. Oof, back. Let's see. Okay, let me check my first derivative. So, first derivative. Oh, I see what they're saying. First part and second part. So this was the. Okay, wait. Okay. Oh. Where is this -5 coming from? Did he combine? He must have combined something. It had to have been this -4 and this. Yeah, that's what he combined. Okay, let me see if I got that too. Negative cosine of x, cosine of x. I should have a. So this should be a -4. Let's see. Okay, so negative cosine of x, cosine of 2x. Yeah, this should have been combined to be a negative. That's what they're saying. Then that would have made this positive. Then that would have meant this would have been -5. But if this is -5, then that would have went to 0. This would have went to 0. I still would have had a -1. Oh, wait. You know what else? I think this would have been negative. So then this would have been a -1 plus a -4, which would have given me a -5. I might have to redo this math though. I got janky. Because apparently there's supposed to be a 4 associated with sine. Oh, I think I see that comes from here. Yeah. Yeah. So this would combine to be 4 sine. That would combine. Okay, so then this would be a, but still, yeah, at x equals 0. Why is it so negative? It stays, which is, it's way smaller. So way smaller. Way smaller. So if the absolute value of f of x is just going to be equal to the function, then what the hell are we doing? That's fine. And I'll just continue on there. That's fine. That's actually a pretty good start. Pretty good start. I'm not mad at it. Let me see. What time is it? 6:37. Okay. And then the next one was these two. Well, I'm gonna have to go do something real quick before I. Oh, I forgot to put problem. Oh. Okay, 2019 A1. Determine all possible values of the expression a cubed plus b cubed plus c cubed minus 3 a b c, where a, b, and c are non-negative integers. What did he mean by that when he said non-negative? I think this one included. Did this one include 0? Yeah, 0 and positive integers. Okay. First thing I would do is we're gonna evaluate kind of like a simpler case. So we're going to evaluate A plus B plus C cubed. And that's where we're starting here. I think that's where I'm going to stop there. Alright, and then last one. Oh my ears. (2018). Alright, this one, find all order pairs. Okay, my thought process here is to solve as my thought process here is to solve as I would any other problem. So I'm thinking we have 1 over A plus 1 over B, 3 over 2018. First thing I'm going to do is multiply the 2018 to the other side. So we're going to have 2018 times 1 over A plus 1 over B equals 3. Then we're going to have 2018 over A plus 2018 over B is equal to 3. Now, what I could do is get a common denominator. Maybe. Or, you know what? This is basically like saying 2018 over A is just equal to 3 minus 2018 over B. And (2018) out of brain fart over B is the same as 3 minus 2018 over A. That's my thought process. So then you could just solve for one to get the other. But it's gotta be an ordered pair. But I think that's what we can do. So then we could take 4 and continue it and have 2018 over A equals 3 minus 2018 over B. We would get, or let me do it like this. Series 4A. Okay. We would we would do A would be equal to 1 over 2018 times 3 minus 2018 over B, which would mean A would be equal to 3 over 2018 minus 1 over B. So that's what A is equal to, apparently. So I'm not the greatest with this. I remember in differential equations I couldn't stand this, where like you had two values and if you solved properly you could figure out one and then plug it in and figure out the other. So we've gotten what A could be. So then could I just go back? Now it's like how far back should I go? Now I'm thinking I go back to 3. And now we do 2018 times basically 1 over 3 over 2018 minus 1 over b plus 2018 over b equals 3. Now I can solve for b. Okay, this is just 1 over. So if I'm not mistaken, oh, and I just did this. You should be able. There was a problem like this in the. It's like the Alberta. I don't even know. The Alberta school. Let me see. There's literally a problem like this. Where is this gonna pop up at? This one. We're basically doing something similar to this. So now I need to do, I'm going to keep this 2018 out. And then 1 over, can we do like keep, change, flip? Like, what does that look like? Keep the 1, multiply, flip to 2018 over 3 minus b plus 2018 over b equals 3. My main like pitfall is sometimes I do stuff that you're not even supposed to do in algebra. I'm just like, yeah, that looks good. Let's do it. But you're not supposed to. Let's see here. Oh, it's fine. I don't really care. All right. Okay. Now, honestly, now we're sitting at 2018 times 2018 over 3 minus b plus 2018 over b equals 3. Okay, now let's do 2018 times 2018. Looks like it, brother. Holy moly. So here we get 4072324 over 3 minus 2018b plus 2018 over b equals 3. And that's the other thing, like, how do you know if you're too far in the weeds? You really don't. It's a lot going on here. Oh, at some point, could I have factor? I think now I probably... Now I can. I think I can factor 2018 out of all of this. So then I would get 2018 over 3 minus b plus 1 over b equals 3. Are we just going to get back there? I'm going to divide that through. 2018 over 3 minus b plus 1 over b equals 3 over 2018. Common denominator? This is rough. This is rough. Okay, wait. I think this is salvageable. 2018 over 3. What do all of these have in common? So this is over 1. We can can we multiply all of this by 3b? Can we do that? Can we multiply? Oh, that's top and bottom by 3b. Is that actually a good idea? Because we can get a common denominator of 3b equals 3 over 2018. This would just need to be multiplied by b, so we have 2018 b. This would need to be multiplied by 3 and b, so this would be minus 3b squared. This would just have to be multiplied by 3. Oh, shoot! That's a quadratic. Oh, shoot. What the frick does that even mean? What do we have? Let me rewrite this. Minus 3b squared, 2018b. Huh. Minus 3b squared plus 2018b plus 3. Isn't cool. Can I factor 3 from 2018? Guess not. What does this mean? I can't keep just multiplying b's. And I can't factor out a b because not everything has a b. Now I'm really stuck. Hmm. Can I split this? Let me try splitting this. Negative 3b squared over 3b plus 2018b over 3b plus 3 over 3b. But even if I do what I'm thinking about doing, that just gets us right back to where we were. Unless I multiply by 3. If I multiply by 3, I might be able to... I think I can't do that. If I multiply by 3, then I would get negative b squared plus 2018 b plus 3 over b, and this would be 1 over 2018. I could then do that because this would have to be, this is some crazy quadratic. And I don't want to multiply that b over there because I would really like to have all the b's together. Okay, I'm stuck. And I don't want to get too far in the weeds, so I'm actually going to stop there for that problem at least. But that's what I'm doing. A little bit stuck in the weeds, but it's fine. I think that's okay. That was horrible. That was fun, but it was just horrible, to be honest. Bro. Let me see. Alright. I think I'm done. I'll probably read the deep learning book off stream. I'll probably go do that after I take a shower and stuff. Okay. Those are the problems. They're just like tacky. Not tacky. That's not good. They're just a little intricate. Or what's the word? Tedious. They're tedious. They're tedious problems. Like upon looking at them, you're like, oh, that's simple. But then once you try and solve it, it's like, that was definitely not simple. Now I'm 16 derivatives in and I don't know where I'm going. That's what it feels like. But all good. I think that's it. Yeah. That's all.